Hello, welcome back to the first course in general physics. In this lecture, we will be talking about the dynamics of a particle, a branch of the study of the motion of a particle. Dynamics of a particle involves concepts such as force and mass, and the principles that describe the relation between force and the motion of a particle are wrapped up in Newton's laws of mechanics. So we will be talking about the forces. What are the forces? The mass, and we will discuss Newton's three laws of motion, Newton's first law of motion, or the law of inertia, Newton's second law of motion, and Newton's third law of motion. Next, we will have an application, an example, applying Newton's laws to the motion of a system of objects. Then we will discuss a special type of forces, which is the frictional force, a very important force in our life. We will go on to discuss the dynamics of circular motion, the motion of a particle around a circular path, and the relation of this motion with the forces acting on the particle. Next, we will go on to discuss concepts of work done by a force on an object and the energy, link these two concepts together. Thus, we will discuss in the beginning the kinetic energy, what it is, what's the definition, the work, what it is, how we define work, how do we calculate it, and we will apply these definitions to calculate the work done by a constant force acting on an object. Then we will move on to discuss the work done by a variable force. Then we will link these concepts of work and energy together, and we will arrive at the kinetic energy work theorem, the theorem that relates the kinetic energy with work done by a force, by external forces acting on the system. Then we will move on to discuss the concept power, which is the rate at which work is done. After that, we will move on to discuss another type of energy involved in the motion of the system, which is called the potential energy. And we will talk about the conservation of energy. In that sense, under this umbrella, we will be needing to discuss what are conservative forces and what are non-conservative forces. We will derive the potential energy and learn how to derive the potential energy of conservative forces. We will arrive at the conservation of mechanical energy, this very important principle. And then we will discuss briefly the work done by non-conservative forces, forces which do not conserve mechanical energy. And then we will arrive at the principle, which is the conservation of total energy, whether it is mechanical or non-mechanical. At the outset, we will discuss the basic concepts related to the dynamics of a particle. So we will be talking about the force and the relation of the force acting on a particle, the relation between that force and the motion of that particle. What is dynamics? A good question. Dynamics is the branch of mechanics that relates force to the motion. Objects around us are acted upon by forces sometimes, and these forces acting on these objects push these objects to move or to change their motion. So the cause of motion of a static object, or the cause of a change of motion of an object that is already moving, is caused by applying a force on that object. Thus, there is a very close relation between the force acting on an object and its motion, the change of its motion and the description of its motion. Before starting the serious discussion of that, we have to remember that objects around us respond to forces differently. First of all, what is the force? A force is an effect acting on an object. It's like a push, like a pull, like an attraction, like a repulsion of some sort. This is the force. When we apply this effect on an object, it responds to this force by moving or changing its motion in one way or the other. But our experience tells us that the response of different objects to these forces or these effects change by the differences of the internal properties of the object itself. Objects are different in a way. So there is one intrinsic property for an object, which is the mass of the object. This is intimately related to the effect of force and the resulting motion of the object. The experiments and our experience tells us that a massive object, for example, would accelerate or change its motion, how fast it goes, and respond to an external force acting on it to a smaller amount than an object that is smaller or less massive. So, for example, if you are pushing a huge table or a huge rock, you will not be able to move it, while if you push a smaller stone, you will be able to move it, but maybe slowly. A yet smaller stone, you can move it very fast by applying exactly the same push. And that small or simple experiment tells us that the acceleration of an object when acted upon by a force is inversely proportional to the mass of that object. So the mass is a property that hinders the acceleration upon the application of a force on the object. When we study the dynamics of an object which moves like a particle, according to our assumption, meaning every part of the object moves in exactly the same way, same direction, the principles which describe the dynamics, the motion of the object under the influence of the force and the relation between the motion and that force, all of these principles are wrapped up neatly in three statements, and these three statements are called Newton's laws of mechanics. So we have three laws, the three laws of Newton for mechanics, and those are the principles of dynamics of a system of particles or a particle. The first of these statements is called Newton's first law, and it states that if no force acts on a body, then the body maintains its state of motion. That is, if the body is at rest, it will remain at rest forever, and if the body is moving with constant velocity, it will continue to move with that constant velocity in the same direction forever. It will never change its state of motion if it is not applied upon by an external force. This is Newton's first law, and this law does not apply in all frames of reference. But before discussing this, we have to define what do we mean by a frame of reference. A frame of reference can be thought of as an object to which we attach our coordinate system. For measurements which are necessary for science, for physics as an experimental science, we need to define a set of coordinates relative to which we make our measurements. And these coordinates are attached, or the system of coordinates is attached to a given body. That body is called the frame of reference. For example, if we are doing an experiment in the lab, and we are making measurements in the lab which is fixed relative to the surface of Earth, then our reference frame is Earth itself, because the lab moves with Earth. It rotates with it, it spins with it, exactly. So our lab would be the frame of reference, which is the surface of Earth. The same, it's on the same state of motion as the surface of Earth. It's fixed relative to the surface of Earth. However, if we are doing our experiments, for example, in a train, in a moving train, then our frame of reference is the moving frame, a train, because our coordinate system is attached to the body of the train itself, and we make measurements relative to a point in the train itself. So that would be our frame of reference. Newton's first law does not apply in all frames of reference. For example, Newton's law does not apply if we are studying the motion of an object in a plane which is taking off, or in a plane which is landing, or in a car which is braking and stopping from an initial speed. It does not apply in a car which we just start to take off. What are those frames of reference that I just mentioned that Newton's first law does not apply in? Those are, as you noticed, accelerated frames. All of them are accelerated. The plane that is taking off is accelerating. It's changing its motion, which means it's changing its velocity, which means it is accelerating. The car that is braking also is an accelerating frame. So this statement, which is Newton's first law, this statement does not apply in accelerated frames. It is applicable in certain frames of reference, special type of frames of reference. Those frames of reference are called the inertial frames of reference. So Newton's first law is applicable only in inertial frames of reference, which are non-accelerated frames of reference. At most, they are either stationary with respect to each other, or they move with constant velocity relative to each other. They don't change the magnitude of their velocities. They don't change the direction of their velocities. Those frames are called inertial frames of reference. And Newton's first law is applicable only in this set of frames, which are the inertial frames of reference. Thus, Newton's law is a statement about the inertial frames. It can be modified, it can be written in a different way to connect with the concept of inertial frames of reference in which they are applicable. So the statement, or the first law of Newton, can be rewritten as: if no force acts on a body, we can always find a reference frame in which that body has no acceleration. That is the reference frame, the inertial reference frame. So this is another way of writing Newton's first law. Second, we come to the second statement, or Newton's second law of motion. This statement relates the external forces acting on the object and its resultant acceleration. The statement is written mathematically in the form summation of F equals ma. The left-hand side of the equation, summation of F, means the sum or the resultant of all the external forces acting on the object. External meaning the forces that are applied by agents that are outside the body itself. So this is the sum or the resultant of the external forces acting on the object. M is the mass of the object on which the external forces are acting, and A is the resultant acceleration of the object. So we can see from this statement that the direction of the acceleration of an object which is a vector, is the same as the direction of the resultant force, external force acting on the object. It's the same direction. And we can see also that the acceleration of an object which is acted upon by an external force is inversely proportional to its mass. So the heavier the object, the slower it goes as it is acted upon by a force. Notice that this summation of F is the net external force acting on the object. This is a very essential point to remember. Notice also that this equation is a vector equation, which implies that it can be analyzed into 3 different equations, each one of them in 1 dimension. The acceleration in a certain direction, for example, the acceleration in the x direction, is caused by the component of the external forces in that direction. So the x component of the external forces would lead to the x component of the acceleration. The y component of the external forces would give the y component of the acceleration, and the z component of the external forces would lead to the z component of the acceleration. So by this, we can use Newton's second law as 3 separate equations, each one of them in general, each one of them correlated with 1 direction of the 3-dimensional space. The third statement, which governs the field of study, which is the dynamics of a particle or of an object, is the third law of Newton, Newton's third law of motion. And this law is concerned with the interaction between 2 bodies. Our experience tells us that forces come in pairs. When there are 2 objects interacting, there is always the first object is affecting the second object by a force, the interaction force, and similarly, the second object is affecting the first object by an interaction force. So forces always come in pairs. Wherever we find an object that is influenced by a force, we can always ask, what is the object, the other object that is affecting by this force? And thus we can always search for the second object that is interacting with our object under consideration. So we can think of the interaction between the 2 objects in terms of an action and reaction. We can say these objects are interacting, and one of them is pulling on the other one is pulling on the other one. So if you are having a rope between you and your friend, and you are pulling and your friend is pulling, there is a tension in the rope, and that tension is acting on both you and your friend. And it is the same force, but in different directions. While it is pulling on you to the right, for example, it's pulling on your friend to the left, the same force. So these can be thought of as action and reaction. This is a common statement that we hear all the time. So this is a picture that demonstrates the interaction between two objects. If we have object A having mass m sub A and object B having mass m sub B, upon interaction, the first object, object A, is influenced by object B by a force F sub A B. F sub A B means the force acting on A due to the effect of body B. And we assumed in this example that this force is an attractive force. We assumed that body B is attracting body A with the force F A B. Similarly, forces come in pairs. If that is true, then body A is attracting body B by a force which is FBA. That means the force acting on B due to the influence of A. So we notice that we have two forces, FAB acting on object A and FBA acting on object B. Those two forces are equal in magnitude and opposite in direction. They could be thought of as action and reaction. A common statement that we hear people talking about is, to every action there is a reaction. This is a common social statement. This statement could involve the fact that cause and effect are involved, meaning that there is an effect that entailed the reaction. So cause and effect could be involved in the social statement, which is like, I became happy because you did that. So the interaction between two may have some sort of an action and reaction, and cause of effect are involved. That is true for the social common statement. However, in Newton's third law, the action and reaction forces are always equal in magnitude and opposite in direction. This is the essence of Newton's third law. The action and reaction, the two interaction forces between two objects, are equal in magnitude and opposite in direction, where FAB, the force acting on A due to B, is equal to minus FBA. FBA is the force acting on B due to A, and the minus sign here is to make sure that these forces are equal in magnitude, but they are opposite in direction. We have to remember that the negative of a vector is the same as the vector, but it's opposite in direction. So the minus sign is to make sure that these two forces are opposite in direction. So this mathematical statement, which is a representation of Newton's third law, says that clearly that the forces that one object acts on the second is the same in magnitude as the force acting on the first object by the second, but the two forces are different in direction. Here we have to remember that cause and effect are not involved in Newton's third law of motion. cause and effect are not involved. All that we have is an interaction between two objects. For example, we have two magnets. The two magnets are attracting each other. The question is, who is influencing the other by the action, and who is influencing the other by the reaction? What force is the action and what force is the reaction? Which one? We have the first magnet is attracting the second, and the second magnet is attracting the first magnet. Which force is an action and which force is a reaction? Nobody can assign such a name to either one of the two forces. Similarly, if two objects are pushing each other away, we apply the same principles and concepts, and we can say that these two forces are equivalent in a sense of the name, and we cannot call any one of them an action or any one of them a reaction. In fact, these two forces are a consequence of the interaction between two objects. If the interaction is cancelled between the two objects, then there will be no forces. Switch on the interaction between the two objects, and then you have these two forces simultaneously. They are a consequence of the interaction of the two objects, and as we mentioned, cause and effect is not involved in this sense. Also, there is another point that we must remember in the context of analyzing the motion of an object, that the two forces, which are the action and reaction, are acting on two different bodies. For one thing, as we mentioned, which one is action, which one is reaction, we can select, we can choose. It's okay. There is no way that we can call a specific force an action and specific force, another force, a reaction, as we mentioned. So we can call any one of them action and any one of them a reaction. Those two forces act on two different bodies. So as we noticed in our example, one force, which is FAB, acts on object A, while FBA acts on object B. They are acting on two different objects. So when we want to analyze the motion of an object, say object A, we would apply Newton's second law, which relates the external force acting on object A to its acceleration. We would apply Newton's second law. We identify the forces that act on object A. And in the case that we have only in the universe, suppose that we assume that we only have object A and object B in the universe, these are the only two objects that are interacting, then we can say that the forces acting on object A is only FAB, F sub AB. Now, this would replace the summation of forces in Newton's second law. On the other side of the equation, we will have M, which is in this case MA, the mass of the object which we are studying its motion, M sub A in this case, times the acceleration. Which acceleration? Also, it is the acceleration of object A. So in a sense, we focus our attention to a given object, and we employ all the principles of motion involved in Newton's 3 laws in mechanics, and we identify the forces. We relate these forces to the acceleration of the body. If the motion is in 3 dimensions, we apply the x component of forces to the acceleration of the x component, and so on, as we mentioned. And we thus obtain the solution for the acceleration. In that sense, we notice that we can calculate the acceleration of an object, both magnitude and direction, or in other words, the components of the acceleration of the object. We can calculate that by knowing the external forces acting on the object. And once we know the acceleration, we can then fully utilize the concepts and equations of motion that we have developed in the previous chapter, which is concerned with kinematics. We can employ these concepts and definitions and equations to fully describe the motion of the particle. For example, from the knowledge of the acceleration of the body, we can evaluate its velocity, utilizing the techniques and the equations of motion that we have developed earlier. And once we know the velocity of the particle at any time, as given by the equations of motion, we can also calculate the position of the particle or of the body at any time. Thus, we know the position as a function of time at any time. We know the velocity as a function of time, and we know the acceleration. And this gives us a complete picture about the motion of the object. Thus, we can confidently say that we have arrived at a full description of the motion of the object. And this was attained or achieved by simply applying these 3 simple principles in mechanics, which are known as Newton's 3 laws of motion. In order to analyze the motion of an object, such as object A in our previous example, we have to draw what we call the free body diagram. This diagram simplifies the analysis. What is the free body diagram? The free body diagram is a diagram that contains the object under consideration as a point mass. So we draw a point representing the object that we are studying its motion, and we can choose a convenient set of coordinates, and relative to these coordinates we can draw the external forces acting on that object. So the diagram that contains the object as a point mass and the axes of the coordinate system used for the measurements and the external forces acting on the body, this diagram is called the free body diagram. It is important to know how to use it in order to be able to identify the forces acting on the object and in which direction is every force acting. One last point to mention in this regard is that when we are selecting the coordinate system, we have to make sure that we are choosing the most convenient set of axes or coordinate system in order to simplify our analysis as much as possible. For example, if an object is moving on a flat table, it makes sense to have the x-axis as the horizontal axis and the y-axis as the vertical axis up, if we are considering motion in a plane. However, if we have motion of an object on an inclined plane, it makes sense to have our x-axis, for example, parallel to the inclined plane, not horizontal, but parallel. That will simplify the problem significantly. So, at this point, I have mentioned what I wanted to mention regarding the basic principles of mechanics, and in the next lecture, we will start with knowing and demonstrating how to apply these to some specific examples. And at this point, I would like to finish this lecture of mine, and I thank you for your attention.